Our group decided to do our project on the turbocharger for an automobile. Materials for the turbocharger can be titanium, aluminum, and stainless steel. The ultimate purpose of the turbocharger is to increase the engine horsepower and to increase the efficiency of an engine. Iteration 1. The first analysis performed was the convection analysis on the turbine side of the turbocharger assembly. The exhaust gas temperature can reach as high as 900 degrees Celsius, so it is important to choose a proper material and thickness so the housing will not fatigue prematurely. Our first iteration here is done with a staggered housing with a thickness of 0.25 inches of cast aluminum. Here is also a model of the turbocharger assembly, as the high revolutions can cause vibrations and infringe upon the natural frequency assembly, so it is crucial to know whether assembly will experience resonance. One thing to note is that the first 6 frequencies are 0 as the modal unrestrained. Another crucial component of the turbocharger assembly is if the shaft with the turbine and compressor wheel, as this shaft can spin upwards of 100,000 RPM, meaning that the blades will experience high centripetal forces. As you can see here, the part fails at the blades of the turbine and the base of the compressor wheel. Iteration 2. In iteration 2, the model changed such that the fillet was added at the base of the turbine and the compressor shaft, as well as the model was changed from a stagger spiral to an inline spiral, and with the larger inner surface area to better withstand the heat, as well as the analysis being from the steady state to transient, in order to better imitate the conditions of the turbine spooling from an engine start. Not only are we concerned with the thermal effects, but also the force exerted on the inner wall of the turbine housing in order to calculate the stress on the flange of the housing, as it is the only rigid connection of the assembly to car engine. Iteration 3. Not only are we concerned with the thermal effects, but also the effects exerted on the inner wall of the turbine housing in order to calculate the stress of the flange of the housing, as it is the only rigid connection of the assembly to the car engine. Iteration 4. On the fourth iteration, the turbocharger assembly was changed such that the material of the compressor housing remained cast aluminum, but the turbine housing was changed to steel alloy to withstand the heat from the exhaust gases. The thickness of the housing was also increased to 0.375 inches to make sure that the temperature of the turbine housing was not 0.4 of the melting temperature, so creep would not occur. The last iteration of the turbine compressor part was a cut across the turbine blade to lower the inertia and to lessen the stress at the base of the blades. The turbine blades were also tapered and a fillet was applied at the end blades as well. Finally, the material of the turbine and compressor blades was changed to a titanium alloy. And here is a modal analysis of the turbine shaft for the first 10 frequencies. Lastly, here are the flow simulations showing the difference between the first and the second models of the turbocharger assembly. In the first assembly, we see the development of an eddy currents as the flow stagnates at the base where the spiral of the housing is staggered. When the housing spiral is in line and the flow is much more streamlined, leading to a good performance of the turbocharger. And here is our cantilever beam. The cantilever beam model was on the end of the shaft where the force was due to the incident exhaust gases on the turbine wheel, which was modeled as 10 pounds. A rigid fixture was applied at the other end on the compressor wheel shaft, and the stress can be observed in the plots. And here is the SN curve showing the amount of cycles that the shaft can endure for this applied stress.